The James Webb Space Telescope just identified a star cluster so ancient that it formed before the Milky Way itself existed, and the chemistry locked inside its stars is a direct chemical record of the universe when it was less than 1 billion years old, containing information that no laboratory on Earth can replicate or synthesize. This is not a metaphor. When astronomers use the word fossil in the context of astronomy, they mean it with the same precision a paleontologist means it when describing a bone preserved in rock. Ancient stellar structures that formed in the earliest epoch of the universe and survived intact to the present day preserve the chemical conditions of their birth environment with extraordinary fidelity. The stars inside them are made of material that has not been significantly recycled through stellar generations. They carry the elemental fingerprint of a universe that had barely begun building the periodic table. The specific discovery generating extraordinary scientific attention involves Webb's observations of a structure designated Sparkler Galaxy, formally cataloged as a system observed at a redshift of approximately 1.38, meaning Webb is seeing it as it existed approximately 9 billion years ago. Embedded around this galaxy are compact, point-like objects that initial analysis identified as young star-forming clumps. But when Webb's near-infrared spectrograph analyzed the light from these objects in detail, a team of astronomers, including researchers from the University of Toronto, determined that several of them are not young at all. They are ancient globular clusters, gravitationally bound groups of hundreds of thousands to millions of stars, that formed approximately 12.5 billion years ago. That age is staggering in its implication. The universe itself is approximately 13.8 billion years ago. These globular clusters formed when the universe was only approximately 1.3 billion years old, before the Milky Way had assembled into its current spiral structure, before most of the galaxy's stars existed, in an epoch when the cosmos was still dominated by the raw hydrogen and helium produced in the Big Bang, with only the earliest generations of heavier elements beginning to accumulate through the first stellar explosions. The chemical composition Webb spectroscopy revealed in these ancient clusters confirms their extreme age. They contain extremely low abundances of elements heavier than hydrogen and helium, what astronomers call low metallicity. In stellar chemistry, every element heavier than helium is technically classified as a metal, and its abundance in a star reflects how many generations of stellar evolution and supernova enrichment the galaxy had undergone before that star formed. Stars with very low metallicity formed early, before many supernova cycles had seeded the interstellar medium with heavier elements. The Sparkler Galaxy's ancient clusters show metallicity signatures consistent with formation in the first billion years of cosmic history. What makes this discovery uniquely powerful is what these fossil clusters reveal about how galaxies like the Milky Way assembled. The current scientific model of galaxy formation proposes that large galaxies grew hierarchically, small structures merging and accumulating over billions of years to build the massive systems we observe today. Globular clusters formed in the earliest epochs of this process are the physical survivors of that assembly history. The Milky Way itself hosts approximately 150 known globular clusters, and a significant fraction of them are believed to have been captured from smaller galaxies that merged with the early Milky Way billions of years ago rather than forming inside the Milky Way directly. By observing a galaxy in the process of actively assembling its globular cluster system 9 billion years ago, Webb is providing direct observational evidence for a process that astronomers had previously only been able to infer from the present-day properties of ancient clusters in our own galaxy. It is the difference between finding dinosaur bones and watching a living dinosaur in real time from a distance of 9 billion light-years. Webb's ability to conduct this analysis rests on capabilities that simply did not exist before its deployment. Detecting the spectroscopic signatures of individual ancient star clusters around a galaxy 9 billion light-years away requires a combination of spatial resolution, infrared sensitivity, and spectroscopic precision that places this observation completely beyond what any previous telescope could have attempted. Hubble's initial observations of the Sparkler Galaxy identified the compact objects surrounding it, but could not determine whether they were young star-forming clumps or ancient globular clusters. That distinction required Webb's spectrographic capability to resolve definitively. The implications extend to understanding the Milky Way's own origin story. If the ancient globular clusters Webb has identified in the Sparkler galaxy are the kind of structures that eventually get incorporated into galaxies like ours, then studying their chemistry, age distribution, and spatial arrangement provides a direct window into the raw materials from which the Milky Way was assembled. Some of the oldest globular clusters in our own galaxy, structures like Messier 92 in the constellation Hercules, estimated at approximately 14 billion years old, and therefore potentially older than current age estimates for the universe itself within measurement uncertainties, may be direct survivors of conditions identical to what Webb is now observing in the Sparkler system. The universe kept these ancient stellar structures intact across 12.5 billion years of cosmic evolution, through galaxy mergers, star formation episodes, supernova explosions, and the continuous churn of galactic dynamics. They survived as chemical time capsules, preserving the elemental fingerprint of a cosmos in its infancy. And Webb found them, read their chemistry, and dated their birth to an era when the Milky Way itself did not yet exist. We now have physical evidence of what the universe's first building blocks looked like, not inferred, not modeled, but directly observed and spectroscopically confirmed across a distance of 9 billion light-years by the most sensitive infrared telescope humanity has ever deployed. So here is the question that should genuinely alter your sense of what we exist inside. If some of the globular clusters orbiting our Milky Way today formed before our galaxy existed and were later captured during mergers, and you could somehow visit one of those ancient clusters and look out from a star inside it, what do you think the universe would have looked like from that vantage point 12.5 billion years ago, when those stars first ignited? Follow this page right now if Webb's discoveries about the universe's deepest history genuinely move you, because we cover every major revelation with the depth and clarity it deserves, and the discoveries are only accelerating from here.